Okay, thank you for having me. Just in the beginning, questions anytime, because it's such a small group anyways, that we can get questions. Like simple questions out of the way first and larger discussion afterwards. So okay, so my title is Advanced EM Field Processing Beyond the Capabilities of Commercial Solvers. And that's a little bit, has always been my philosophy. You've got all those electromagnetic solvers, and there's a lot of them. You've got CST and SEMCAT and XFTTD and whatnot. And over the years, they have slowly started to cater to the MRI community, have some features that are more MRI-centric, by what my thought was always that doesn't really make any sense because it's so simple to just do it on your own. And so today I'll talk a little bit about some things that you can easily do. For example, in MATLAB, as long as you have the files, and some techniques that will give you a better overview of your coil, and it's focused on multi-channel coil arrays for transmit as well as receive. Okay, so yes, that's just what I basically said. It's pretty bad for MRI-specific post-processing, because MRI is still in comparison a relatively small community. I know CST is doing is getting there a little bit, and yes, the analysis of complex multi-channel coil arrays. Whoever tried that just in the EM suite alone had a bad time, but it's really simple to set something general up using MATLAB or Python or whatever to just do what you want. So everything I'll discuss will just need those things that you can get out of every program out there, at least the ones I know. CST will give those to you, all the field data sets from your simulation. You get the mesh information, so the geometry information. You need the material conductivities. Alternatively, you don't need even those, because you can just get them by dividing the current density that you get out of the simulation by the electric field. And then you've got your tissue conductivities, for example. You get the scattering matrix out of your simulation, and you also can get the voltages and currents through all the lumped elements that you have in your simulation out there. So I have three parts here. So I'll first start talking about power balance framework that kind of sits in the background of many of the later analysis. So that basically talks about how can we conveniently have a look at losses that occur in the coil, but especially in the context of coil arrays, where it gets a little bit more complicated. Then the second thing will be the Eigenmode analysis of coil arrays. So it's nothing really new. It's basically relatively old looking at coil arrays like this, but I don't know why, it's seldom used in that context. And lastly, I will come to SNR analysis and maximum efficiency V1 shimming analysis, and how you can easily do those. So let's start with the power balance. Everyone has seen those types of diagrams. So you put some power into your coil, it gets dissipated somewhere. For a single channel coil, that's really simple, of course, because you've got a certain percentage that goes into the load and a certain percentage that goes into the rest of the structure. But for multi-channel coil arrays, it's a bit more complicated, because there it depends what kind of excitation you are using on your coil. For multi-channel arrays, you can just write any of those loss terms. For the single channel, it's just a number or percentage, and for the multi-channel, you can just write it as a quadratic form. V is a vector of your excitation voltages you put into the coil. So just contains the amplitude and phase that you put into each channel. And Q is a so-called power correlation matrix that you can calculate from the data I just showed for each of those. And Yes, it's the, that's should be in the bottom, P, source, so the source power. So what really goes into the coil is basically just the forward power, that's the power that's coming from the amplifier, minus the power that goes back from the coil array due to reflection or coupling. The whole point is using the field data. Yeah. Look, I invented new. Those are not quantum mechanical lattice operators. It's ladder operators. No. The thing is using the fields and the currents and voltages. What you can do is construct a set of matrices and exactly one matrix for every loss mechanism that you want. You can construct one matrix for the losses that occur in all the capacitors, and one matrix for the losses that occur in the body, and one matrix for the losses that get radiated away, and so on. And they all, of course, have to sum together to the power that you originally put out from the amplifier because of conservation of power. And it's nice to have them in matrices because then you can just do standard matrix analysis techniques to look at, okay, how does my coil array behave under certain conditions? And that's not really the main point, but we are always going to come back to those formulations from now on. And the first really big topic is the Eigenmode analysis. So you all know birdcage coils, I guess. And you know that the birdcage coil have a set of specific modes where we are usually interested in the lowest or highest order mode, depending on if it's a low or high pass birdcage, but that's the one that's the homogeneous mode. So, but now what about other arrays? Let's say you've got just some kind of array and you just want to know, okay, how is this working? Are there some modes I can drive this array in that somehow stand out? Yes, that are something equivalent to what I see in a standard birdcage model. And those would be the so-called eigenmodes of a coil array. And the eigenmodes are defined as giving you field profiles that are orthogonal in some sense, and the point is you can have that you are aware of the notation of the orthogonality. You can, for example, say that the integral of the electric fields, so you've got electric fields from one mode of excitation and electric fields from another mode of excitation, and you can say they are orthogonal if this integral is 0. And you can do the same thing for the B1 field as well over the sample. So let's just have a quick look at just a simple 8-channel coil array that looks like just any standard head coil geometry that you would get for parallel transmit experiment. You've got 8 channels. They are decoupled with those little transformers, and we're at 7 Tesla frequencies, and we just previously, as I talked about the power correlation matrix, we had one matrix that contained all the samples, the losses inside the sample. And turns out, if you calculate the eigenvectors and eigenvalues of this matrix, that those are exactly those electrical eigenmodes. And looking at them, oh, that's wrong. You see that you get put 8 channels, and you get 8 modes out of it. And those are for the 8-channel array. They look exactly what the mode profiles look like for the normal birdcage resonator. But they're all at the same frequency, of course. The birdcage, they are at different frequencies, every profile, but what you have here is just those 8 modes with different profiles. And what is the really helpful thing at looking at an array not from the perspective of the single channel B1 maps. I mean, everyone sees those in their solver. You can have a look at the single channel B1 maps, but that doesn't really tell you anything about how your array performs globally over your whole sample. So that's why you can just look at it on the basis of those modes, and you see, okay, those 2 modes, they give me sensitivity in the center. And here I can see I get nothing in the center from those modes. I only get some signal in the periphery. The same here, I get more signal in the periphery, and I get more signal in the periphery. And that's exactly, it's one of the basic properties of the coil arrays. You can add more elements and more elements. And all you get is more peripheral SNR increase. And now that's a very simple model because it's so well known. It's basically a birdcage coil just with a single element. So those mode profiles are very well known. But the real usability is when you have a novel idea, some coil that you dreamed up, and you want to know, okay, if I put it in the scanner, how do I want to drive it? Oh wait, I come to that a little bit later. Next, let me go back. We see those mode profiles. And now getting back to the power balance, it turns out that each of these modes has a different loss structure. For example, we see those 2 modes. They deposit something like 70% of the power in the phantom, so that's not too bad. And the rest of the power goes mainly into the tuning and matching capacitors, and a little bit into the decoupling inductors, and very little is lost because of the coil interaction due to the coupling. So now we go to those 2 modes, those that look like the linear birdcage modes, and we see, oh, they're not that good. They have a lower power deposition in the phantom. And what we can see, those are the only 2 modes where power is radiated out of the bore. So all the other modes, there's basically no radiation loss. That's shown in gray, but these 2 modes have radiation losses. So, what does it help you? It tells you that, well, if I want to increase the sensitivity of my coil in the center, I better do something more about the radiation losses. So I don't want the power leaving the bore. So maybe I have to modify my shielding of the coil. And the same goes on for these modes. You see the 5, 6, and 7, and they give you SNR in the periphery, but they are really dominated by the losses in the coil. So you want to bring down, maybe use better capacitors in your coil elements, and that will benefit those modes that give you sensitivity on the outside more than the sensitivity in the center. So you can have a look, okay, where is the ROI, where I'm interested in, where are the losses coming from in that area, and what do I have to do to counter that? So, as I was saying before, let's say, yes?
This one is normalized value, right? As a 100. I just previous one is just 100% as a normalized.
Yeah.
So Is there any different mode has different kind of, for example, one mode is actually the efficiency is maybe higher than the others, or
What do you mean with yes, I mean, what's really efficiency here is power that goes into the phantom, because everything else is lost, right?
This scale is transmit efficiency scale,
Yes.
right? Okay, then.
Yes, it's transmit efficiency. So for those, you are very efficient, and for those, you are not very efficient. The red is
actually it's my question is this is what they are 100%. So means your power is only you only send 100%, and then you calculate this how much is.
yes, calculate how much goes where.
Okay.
It's normalized to
Because I just thinking whether it's possible to, if you apply here it's 150, and the other one is, I mean just say.
but you always have the same power going into the coil.
No.
So you always put 1 watt into the coil,
Okay.
and
Okay.
Because
where
no matching is changing by this condition.
no, nothing
Yeah,
nothing is really changing. But moving on, let's say you have a nice new idea for a coil which you want to try out. For example, something like this. That was a coil I had in Berlin. I didn't build it, but someone else did. So that's a funny coil so that's the edges of an octahedron, and there you've got those current sheet antennas there, and that has got a funny geometry around. So how do we understand this coil? So you can simulate the coil, and you can see that's just an axial slice in the XY plane. You can see how the B1 field looks from all the channels. Okay, that's nice that you can get out of every solver, but it gets much more interesting when you now have a look at those modes, because what you now have is basically the equivalent of the fundamental birdcage modes for this coil. And you can see that this octahedral coil has 3 homogeneous driving modes that you can use, and it's got 4 more modes that give sensitivity in the periphery, and the rest is basically nothing. So we have a 12 channel coil array. When you really look at it, the only thing that's really usable is 6 channels. So you're, of course, you don't have 12 coils that generate orthogonal fields. You will always get a lower number of usable modes, but for that case it's really bad, because basically what you get is only half the number of usable channels, and that, as we will come back a little later on, will also impact the parallel imaging performance there. But
One question about the eigenmodes. Did you mean that the CP modes?
yes,
But usually you have the positive and this negative CP modes. Did you mean just the positive modes with this 12 eigenmodes? Or
oh yeah, well, you can, that's the, yes, of course, you can always have also the counter rotating one, but
Okay.
that's just,
it's a clockwise rotating one.
that's the clockwise.
Okay.
Yes.
Okay.
That's for transmit efficiency. Exactly. So you can see this way, you can have a way to judge, okay, how many channels do I really have with my array? And it's not only for transmit, you can do that for receive purposes as well, and it's equally well. What is related, and anyway, before we calculated those eigenmodes based on the electric fields, and now we can do the same for the B1 field distributions, and that is again for the 8-channel coil array we saw before. That's what we get out there. That's now a little bit different view. We see we've got, that's the homogeneous mode that we are looking for. It's a normal CP birdcage mode. And then we have again the sensitivity in the periphery. And again, we see, and we saw that before, we've got something like 7 modes that look nice to use. And it's interesting to note this homogeneous mode, is basically just the sum of those two. And the other one that had sensitivity in the periphery is just the sum of those two equal ones. And the third one is the sum of those two, and so on. So you've got a really close relationship between between the magnetic and electric fields, but it gives you a little bit different views on it. And let's do it again for the 12-channel coil, and here we see the same image. Yes, we've got the homogeneous mode, that's now the sum of the first 3 electric of the homogeneous eigenmodes. And then you can see, okay, in the periphery, we have some modes that give us sensitivity there. But yeah, maybe this can be seen as something that gives a little bit of contribution, but really, that's just nothing. And again, we see we've got 12 channels, but it's really not that useful. And you wouldn't really see that when you just look at the single channel fields, because that just doesn't tell you that on that level. So I'll skip that part because it's not so important. So, but we've seen that this eigenmode calculation, and they were presented in 2004 or 5, I think, for receive arrays. They are very helpful, and in conjunction with the whole power analysis, what you can easily see is, okay, I want sensitivity in this region. These modes give me sensitivity in that region. The most important losses I have in those modes are this and that. So when I reduce losses in those components, I will get better sensitivity in that area. And that's really helpful when you are in the designing stages of your coil. So let's now go to something that is more receive-only centric, but also applicable for transmission. We have again wrong formulas. When I started looking into some optimization techniques and so on, I once again stumbled over the fact that everything we are doing has been done by the people who do phased array antennas in the 70s. So there are so many papers that claim to have, okay, we solved this really complicated problem, and then you look at it, and then you search through the literature in the context of phased arrays, and then you see, oh, someone in the 70s calculated that already. So that's really something when you have a problem with array coils and optimizing something there with amplitudes, phases, whatever. Have a look at the antenna literature. They have solved all those problems and much more complicated ones already. But we are talking about two things that are really the same. Imagine, firstly, you've got a coil array, and you want to reconstruct your image. And to do that optimally, you have to take the noise correlation into account. That was in the very first phased array paper by Römer already. And the second scenario you have, for example, for a transmit coil, is you say at this one point, I want to have the maximum possible B1 field. And both those problems are basically the same thing, because you've got the amplitude of the B1 field. Let's say we have at one point we can construct a vector B, and that contains just all the B1 field values that each coil has at that position. So it's just a vector with the elements B1 field of coil 1, B1 field of coil 2, B1 field of coil 3, B1 field of coil 4, and so on. Okay, and so when you want to combine the signals for reception from all those coils, you have to apply a scaling factor to each of them before you add them together. And let's call that again V. And since this is a scaling factor and we want the magnitude of it, why don't we multiply it again with itself? Like this. So we've got a vector. So this is just the scaled the dot product between the scaling vector and the B1 vector, and we multiply it by itself, complex conjugated, and then what we get at that position is just the B1 squared that we get from the combination of all the B1 fields with the combination vector V. So, but for reception, what's the problem? We also get noise. And what do we want? We don't want maximum signal or something. What we are interested in is maximum signal to noise ratio. That's the signal part. The signal is proportional to the magnetic field, to the B1 at that position, but we want to maximize the ratio of signal to noise. So in the denominator, we need an expression for the noise power. This is basically magnetic field energy, and this is an expression for the noise power. And so this Q, that's just again one of those power correlation matrices or noise correlation matrix, and we want to maximize this. And just put the brackets around here. We've got a matrix there as well. So basically we are maximizing the ratio of those quadratic forms, and no one uses, you see it in many publications, but no one uses its actual name. That's a Rayleigh quotient, and it's been solved a long time ago. Everyone knows that, but you never see this specific name mentioned. And once if you look for maximize ratio of quadratic forms, you find a handful of papers, and then you take Rayleigh quotient, and then everyone has solved it under funny constraints and everything. The thing is, we can now, since it's the important part anyhow is that we know the solution to this, and that is basically this. We've got the inverse of this matrix there, and that's basically the sum of squares reconstruction that everyone does. And this is the inverse noise correlation matrix. Now, but how do we put that to use in the simulation? Okay, and how we put it in use in the simulation is how we choose which matrix Q we choose here. We've got all those power correlation matrix. Now I've got a coil array, and now let's say I want to know the SNR. What SNR do I get out of my coil when I do a proper reconstruction? And I can get something like this when I calculate it. Okay, So I get more SNR in the center, in the periphery, and less SNR in the center. Okay, that's all nice. And I get that by choosing this Q to be just the forward power minus the reflected power. That's basically all the losses summed up. That's losses in the sample plus losses in the capacitors, and so on and so forth. And I get something like this. But what I'm really interested in when I simulate my array is how close do I get to the optimum? And what's the optimum? The optimum is when I have no other losses except the sample losses, because I can't control the sample losses. I can't get rid of them, but I can build a coil out of less lossy materials. And when I calculate this optimization with just the losses that occur in the sample, I get something that looks different. That's with all losses, and that's the SNR I could get if I didn't have any extra losses. And when we look at the ratio, okay, in the center I get something like 70-something percent, maybe 80%. Okay, and in the periphery it drops down to 60%. So using that, you can easily judge, okay, I've got a coil array, it could be this good if it was perfect, but how close do I get to perfect with the coil? And once you calculated that, you can even have a look at where exactly does the noise come from in a specific region of my image. I can, for example, say that in the center of my image, when I look there, okay, the total noise is dominated by what really comes out of the sample. It says body here, but it should be phantom. There is very little from the copper, very little from the inductors. But, for example, radiation losses, so some noise that comes from outside of the bore, is also very strong in the center. And in the periphery, we are, again, the noise is dominated by the noise from the capacitors and the plastic we have, and so on. And again, we're always interested in doing that for some novel coil arrays that are not so easily understandable. That's for that 12-channel coil array where we don't have to go into the details, but we can see that in the realistic case, we get very much worse than the optimum case, and we have got those two very, very strong dropouts and two portions of the phantom where the theoretical maximum would be okay, but where in reality we get just very low signal to noise. And okay, we can have a look why that is. Okay, main losses come from the capacitors, which are really bad in that coil. Of course, there's only one, and there are also radiative losses, and that would be noise that's coming from outside the bore that's dissipated there and comes into the bore as noise. And so for the last part, we can, the same thing is basically when you do B1 shimming, when you're interested in, okay, how much B1 do I really get for my power at a specific position? You can just calculate the same thing. You just take B1 plus instead of B1 minus, and for that 8-channel coil array, we see, okay, in the center, I get something like 20-something microtesla per square root of kilowatt, and that's forward power that goes out from the amplifier. In the periphery, I can get something like 40 microtesla per square root of kilowatt. But if I have enough amplifier power, what I really should be worried about is SAR. So what goes into the patient, because I don't really care about the rest. And if we really looked at that, we can actually be much better, because we can, when you look at it, you can get more than 30 microtesla per square root of kilowatt absorbed power, so this power that is truly going into the phantom. And in the periphery, you can even get up to something like 70. And that's what, in the end, when you're doing a real experiment on the scanner, should matter, because who cares about all the losses that don't go into the patient? That's not your limiting factor. You're limited by SAR and maybe by the transmit power. But this again gives you a nice global overview of how the coil array can perform, not just based on the single channel fields, but actually on a global scale. So, and this is basically the same thing for transmit and receive, and it may all look quite complicated now, but I assure you it's not. For example, the whole power balance code, I'm happy to share that. And calculating the SNR maps we've seen is a one-liner in MATLAB. So it's just as an example that you can basically, in one line, you get those maps, and calculating all those things takes computational time of something like less than a minute. And it's something that you can easily, more or less, do yourself and don't have to wait for some manufacturer implementation in their solvers, because that's basically never going to happen. Yes, if you want something done right, do it yourself. That's yes, and that's basically that was just an thank you for your attention, and that was basically just an overview of what you can do besides look at just some field distribution in your solver to get some more insight.
Thank you.
Thanks.